everybody, and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. And this is lecture number 2 on wave particle duality. So, in our previous lecture, we had seen the basic evidence of energy quanta in terms of the frequency of the incident radiation. And Planck's hypothesis said that energy is quantized or has got a fixed value depending upon the frequency of the input light, and he gave the value to be equals to h into nu, when nu is basically the frequency of the incident light. Now, you can also write that to be as hc by lambda, where c is the velocity of the light. Nu can be replaced by c by lambda. So, higher the wavelength of the incident radiation, lower will be the energy of the incident light, right? And we also saw the concept of work function, which means that there's a minimum critical value of energy beyond which there will be a linear increase in the value of the maximum kinetic energy of exiting electron with respect to the frequency of the incident photon. So, the discreteness of energy was first involved by the concept of photoelectric effect, for which Einstein got a Nobel Prize. Now, the next concept which came into picture was that of wave particle duality, and I will tell you, rather than going into much more mathematics of it, at least for you to understand enough to go ahead and do the cryogenics, is that in subatomic region, electrons are not taken as particles, but they are taken as wave. So basically, there is always a duality between wave and particle, right? And how you are measuring it, depending on that, the particle will behave as a particle at some point of time, for example, photoelectric effect, and will behave as a wave at certain other point of time, for example, when you do some diffraction or interference pattern using electron diffraction, right? So therefore, any particle in quantum mechanical domain will behave like a wave or particle depending upon the experiment or the way you are observing the particle. Now, if you look at the particle, when we know that the particle will have a position in space and time. However, if you look at the wave will have, let us suppose I have a continuous wave available to me, and therefore with respect to time and space I can draw a wave equation, and from the wave equation I can predict probability of finding the particle within point A and point B. So, dual nature of light was first in a sense given by this experiment known as Davison and Germer experiment, where the scattered electrons were having different lambda as compared to the incident electrons, which means that there was a change in the lambda between the wavelength of the input electrons and the exiting electrons. And then finally, the wave particle duality was also closed by de Broglie hypothesis, and he said that if p is the momentum of the particle, then the corresponding de Broglie wavelength lambda is given by h by p. So, lambda is given by h by p, where p is the momentum. So, this is h into m into v. Again, please understand this, these are all subatomic particles, right? So, this m value will be very low in a sense, right? H is of the order of minus 34, m will be of the order of again minus 34, 35, and therefore higher the velocity of the charged particle, lower will be the value of lambda, and lower the value of the velocity of the charged particle, higher will be the lambda value. Lambda will therefore will be with respect to a particle. If I define a wave, then the lambda is basically divided as the wavelength of the particle, which depends there on the velocity of the particle. Now, the experimental confirmation which came of the wave particle duality was through electron diffraction experiments, as well as one was example was very simple. It was the double slit experiment, where interference patterns were developed because electrons coming out from some input and is going through a double slit of experiment. So, you had two slits which is available here, and the electrons were coming from this end. So, ideally the electron either can pass through from slit number 1 or slit number 2, but what people saw was that if you have a pattern being generated, you have these patterns of alternating high electron density and low electron density patterns. This was obviously not justified or not explainable if the electrons were considered as particles, right? Because if they were discrete particles, you will find at discrete regions of at only two places, right? Either you will find it in front of 1 or in front of 2, because that's where you will get the maximum probability of finding the particle. And therefore, a sort of layman way of looking at it is that when the electrons flows through them, rather than it electron, it's basically as a wave. When the wave passes through slit number 1 and slit number 2, it actually interferes and gives you the position of high density of electron, and it also destructively interferes to give you low density of electrons here. So this was one of the experiments where wave particle duality was explained. So which means that at low subatomic particles, two things are important. One is of course your quantization of energy, and the second is the wave particle duality. There is always a duality between wave and the particle. So I'll just end this subsection by giving you a small example. So we need to calculate the de Broglie wavelength of a particle, considering that there's an electron which is traveling at 10 to the power 5 meters per second. So I have an electron which is traveling at the rate of 10 to the power 5 meter per second. It's again a subatomic particle, and therefore you are told to predict the value of lambda, which is the de Broglie wavelength associated with it. So we already know that the momentum of the particle is mass times velocity. This is the mass of the electron, 10 to the power minus 31, multiplied by the velocity, 10 to the power 5, and this comes out to be 9.11 into 10 to the power minus 26 kg meter per second. Now lambda, the de Broglie wavelength we have already seen, was h by mv. H is the Planck's constant, which is given by 6.625 into 10 to the power 34, very important sort of a constant in quantum mechanics, and this comes out to be 7.27 into 10 to the power minus 9 approximately, which is lambda is equals to 72.7 angstrom, which means that if I have an electron, discrete electron traveling at 10 to the power 5 meter per second, then its corresponding wave will have a lambda wavelength of 72.7 angstrom, right? Now if you obviously, as you can see from discussion, if you go on increasing the value of this speed 10 to the power 5, 10 to the power 6, 7, 8, 9 and so on and so forth, your lambda will still go on decreasing, right? The wavelength will go on decreasing as you move to a much higher velocity, right? And therefore from here you can predict the availability of particle. So this is basically a numerical approach to showcase to you that how we can actually calculate the value of the de Broglie wavelength of an electron passing through any region of operation. Similarly, if the mass of the particle is changed from electron to proton, then also your de Broglie wavelength will reduce, because the mass of proton is relatively larger as compared to that of electron, and therefore the lambda value will actually reduce in that case. So higher the velocity or higher the mass, you will have a reduced value of de Broglie wavelength with you, right? Now let's come to the third principle. So we have done with energy, we have looked into wave particle duality. Let's come to the third principle, which is very different from classical world, and this is known as the uncertainty principle, and it was actually developed by Heisenberg. So it is referred to as a Heisenberg's uncertainty principle, right? Now this is quite interesting phenomena, and only again visible or justified at very low sort of dimensions. They are not applicable for large dimensions or where classical dimensions are there. Now what does uncertainty principle? Let me read out the statement, and then we will discuss each one of them individually. The uncertainty principle states that for certain pairs of physical properties of a particle, such as position and momentum, there exists a limit to how precisely both properties can be simultaneously known. This is the statement which Heisenberg gave. So if I take any two physical properties of a particle, right, and these are known as conjugate properties, for example position and momentum, then the problem is, according to the Heisenberg uncertainty principle, the problem is that if you are able to with 100% accuracy find out the position, you will not be able to find out the momentum with 100% accuracy. In fact, it will be infinitely uncertain. You will never know the momentum, or vice versa. If you know the momentum very well, your position will not be known, right? And therefore the statement which Heisenberg gave was delta x into delta p is greater than or equal to h cut. H cut is a modified Planck's constant and is given by h by 2 pi, right? You can see here this is h by 2 pi, and it is given by this value here, that 1.054 into 10 to the power minus 34 joule second, and it is referred to as a modified Planck's constant. Now let's look at first of all this expression here, which is this one, and then we will give a physical definition or a physical understanding of it. It tells me therefore that if del x was equals to 0, so let me find out like this, my delta p will be greater than or equals to h cut by del x. So now if my del x is the uncertainty in position And if that uncertainty in position is equals to 0, which means that I am able to accurately see the position of the particle, it effectively means that my delta p will tend to infinity, which means that I will not be able to measure the momentum, right? My error in momentum will be infinitely large, which means that I will not be able to at all measure the momentum of the particle moving in a plane, right? And vice versa, if you look at the momentum, similarly, if delta x is given as greater than equals to h cut by delta p, if your delta p equals to 0, your delta x also tends to be infinity. And therefore, if you're able to very well know the momentum of the particle, you will not be able to find out the accuracy of the position. Yes, it will go to infinitely large. Let me explain to you physically why and how is it, and let me show you how does this work out. Now, the idea here is that let us suppose I have an electron which is moving in a circular orbit across a nucleus. So I have a nucleus, right? I have a nucleus here, and across the orbit in an elliptical path, an electron is moving, assume it to be counterclockwise or clockwise. So how will you try to know its position? You can know its position by looking at it, right? So I'm saying in a very simple language. So if I want to know a position of a person walking in the road, I need to look at it physically, right? And then compare his position with respect to some stationary object, and we say that okay, this is the position of the particle and this is the velocity of the particle which is moving. However, when you look at subatomic or atomic particles, you cannot physically look at it, but you require to have an external source to look at the electron. Let us suppose I shine a light, and the light gets stuck at electron, reflects back, and I'm able to see the position of the electron using that light, right? But while doing so, you ended having giving some extra energy to electron, and therefore the momentum of the electron will change suddenly. So you see, though you are able to exactly or accurately measure the position of the electron with respect to the nucleus, the very fact that you want to measure it accurately has actually changed the value of the momentum of the particle drastically. And that's from where your Heisenberg uncertainty principle came into picture. Now, since obviously this is not explainable or justified at classical limits, for example, where the dimension of the particle is very large, because you can see that the reduced Planck's constant is of the order of 10 to the power minus 34. So let me give you an example in this case. So what will happen is delta x, if you want to find out the h cut by delta p. Now this h cut will be therefore given by 1.054 into 10 to the power minus 34. Let us suppose I want to find out delta p, then this will be delta x here. So let us suppose my delta x is of the order of a few angstrom, let us say 10 angstrom. So 10 into 10 to the minus 10. So if you do all sorts of manipulation, or maybe I write 1 angstrom, let me assume it's easier. So this will be 10 to the power minus 24 delta p. So you see, your accuracy of or uncertainty in position was 10 to the power minus 1 angstrom, and therefore the position uncertainty was actually equals to of the order of 1 into 10 to the power minus 24, this thing, right? Go on increasing the value of delta x, and you will actually go on reducing the value of delta p, such that the product is approximately equal to or greater than the reduced Planck's constant. So uncertainty principle in few words is very simple and straightforward. Two things in this, I have shown position and momentum, but another conjugate pair is energy and time, that is one. Angular momentum and angular position, these are all conjugate pairs which cannot be properly ascertained using the conventional techniques, only applicable to low dimension devices. So let's look at the application of uncertainty principle, right? The first one is quantum tunneling. We will come to that after this. Next one is of course the de Broglie hypothesis, which we have already seen, and the experimental confirmation of de Broglie hypothesis comes from electron diffraction and interference pattern, right? Now let me give you the concept here, the same concept of uncertainty principle. You see, in a classical world, if let us suppose you have this big tall sort of a rock or a big rock, so the potential is quite high, which means that if you want to throw a ball to the other side of this wall, you need to at least give that much amount of potential energy, which is this equal to mgh, this one, and also a kinetic energy to throw it across it on this side. So in the classical world, right, in the classical world, this is what will happen, and therefore as you can see Therefore, if the energy levels are smaller than the potential energy required to cross the wall, there will be zero probability of any ball to be thrown by a person to reach on the other side of the wall. So then it's a classically forbidden state available to me. Whereas if you now have a quantum ball and all the dimensions have been reduced to quantum dimensions, there will be a small probability that the quantum ball will tunnel through this layer of wall and then reach on this side here. Classically not possible, quantum mechanically there, right? Now, so we had already looked into the fact that delta x, delta p is greater than or equals to h cut. Another way is delta E dot delta T is greater than or equals to h cut. What does it mean is that if you have a particle and you want to measure its in time domain, where is it, and you measure it exactly properly, you won't be able to measure the change in the with accuracy the energy of the particle. So time and energy happens to be the two sort of conjugate sort of properties where Heisenberg uncertainty principle is applicable. So let's understand therefore one important point, that this concept of tunneling, that there's a tunneling of subatomic particle through a region where the potential is relatively high, but there's a finite probability the particle, which is quantum particle, can tunnel through this region and reach to the other side, right? So this is the difference between a classical and a quantum theory in a sense, right? Now let's come to quantum tunneling in a sense of it. So as I discussed with you, if energy is less than u naught, where u naught is the classical energy, potential energy, if E is less than u naught, you will never have an electron coming out of it on this side. It's a forbidden state. However, if you consider subatomic particle, there will be certain probability of finding electrons on this side. I will show you what do I mean by all these things. These are basically the wave functions, right? And depending on the value of the wave function, you can find the probability of finding the particle. What we have learned therefore is, we will not go into mathematics deeply at this stage, but if there is a quantum mechanical tunneling happening, then it basically means that a subatomic particle can cross a barrier and reach to the other side of the barrier, provided and with certain probability. It will always reach, no. It will always not reach, again, no. So there will be always a probability associated with the particle's transmission through the potential barrier. This one is known as potential barrier. Okay, so this is the quantum tunneling of electron wave function. We have already seen what is the de Broglie hypothesis, that the matter and wave are associated with each other. Electron can both behave as a wave and as a particle in places. This only depends upon how we are actually looking at electron, right? And one example of electron as a particle is basically your photoelectric effect. Another wave equation is basically your double slit experiment, which is there, right? And that gives you the basically the de Broglie hypothesis that wave nature and the particle nature are dual nature of a subatomic particle. Now to finish this lecture, I can show it to you that I have wave nature of particle, which gives you interference and diffraction. And if it's a particle nature, then we will have discrete particles at discrete positions within the space, right? If you look at the wave nature of the electron, then it is supported by electron diffraction and double slit experiments. Whereas if you look at the particle nature, photoelectric effect and Compton scattering is another of them. I will recommend that you study quantum scattering from any class 12th or even class 11th books. You will have a basic look of what is known as Compton scattering. In wave nature, electrons obviously can interfere with themselves, whereas if you look at the particle nature, they will not interfere with themselves. They follow distinct trajectories and different particle paths for it, right? So these are the three major differences which we look into, the differences between them. Let's come back to the energy scale. If you look at the wave nature, then energy is distributed continuously in a wave nature. In particle nature, the energy is always quantized and there are discrete energy states which are separated from each other by discrete quantities. And it is forbidden to have any particle in energy states between discrete energy states. For the wave nature of electron, we have associated de Broglie wavelength depend h by mv, where v is the velocity of the particle, and it behaves like a wave. Whereas in a particle, obviously de Broglie wavelength has got no meaning, and therefore electrons are treated as particles, right? Wave nature, obviously energy is distributed, whereas it is quantized in case of particle nature of electrons. So let me recapitulate what we learned for the previous half an hour. Let me give you a brief idea what we learned. So we learned about very important principle of uncertainty. So this was Heisenberg's uncertainty principle, and it tells me therefore that del x del p should be greater than equals to h cut, del E del T should be greater than equals to h cut. Then we went into de Broglie wavelength, and it was given by h by mv. H cut is equals to h by 2 pi. This is a modified Planck constant, and therefore this is known as de Broglie wavelength, and this de Broglie wavelength is therefore related to the frequency of the particle, right, and also depends upon the mass of the particle, again subatomic particle. Then finally we looked into quantum mechanical tunneling, and we saw that quantum mechanical tunneling will allow you to pass the electron from point A to point B. Even if there is the potential is very high, you can find a probability of finding electron on the other side of the barrier. And then finally we distinguished between the wave nature and the particle nature of the subatomic particle, and we were able to take care of all these things in a better manner. So with this, let me stop here today. Thank you very much.